Hello, this is question 3 from the 2016 math. So in this question, we fix a real number alpha, which will be the same throughout. We say that a function f is bilateral if f of x equals f of 2 alpha minus x for all x. Part 1, show that if f of x is x minus alpha all squared for all x, then the function f is bilateral. So we've got f of x equals x minus alpha all squared. F of 2 alpha minus x is 2 alpha minus x minus alpha squared, which is alpha minus x squared. So that's minus 1 squared times x minus alpha squared, which equals f of x. Right, that was a nice start. On the other hand, show that if f of x equals x minus alpha, so we're not squaring it, for all x, then the function f is not bilateral. So in part 2 then, we want f of 2 alpha minus x equals 2 alpha minus x minus alpha, which is alpha minus x, which is not equal to f of x. Right, they started us off fairly friendly fashion there. Part 3, show that if n is a non-negative integer, a and b are any real numbers, then we've got these integrals related in that way. Well, I think we just do the integrals. Looks like the way to go. These are pretty simple integrals. So the integral from a to b of x to the n dx is going to be x to the n plus 1 divided by n plus 1 from b down to a. So that's b n plus 1 minus a n plus 1 all divided by n plus 1. Then let's do the next one then. So minus, we're doing the same thing, but this time b to a. I mean, we know this is true. It seems like a really weird thing to get us to show. Don't forget the minus sign there, because we do this all the time, flipping these limits around and putting a minus sign there. Oops, put them the wrong way around myself on that one. So that means we're going to get minus a to the n plus 1. That should be a minus b to the n plus 1 over n plus 1, which equals b to the n plus 1. I keep putting plus in the middle. Minus a to the n plus 1 over n plus 1. Right, so that's what they wanted. QED. Last part, hence show if f is a polynomial and a and b are any reals, then the integral of f of x, so these integrals, but now they put f of x rather than xn in there. They've just flipped these things over. Well, of course you're going to get that with polynomials, because f of x is going to be, say, well, a plus bx plus c x squared plus dot 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 all the way up to, some whatever, with an x, well, x to the n, whatever we're going to have on there, with some letter in here. I don't know, I'm going to run out of letters, and so I'll just call it a beta at the end. So if we then integrate this, we can say the integral of f of x dx from a to b is then going to be the integral of a from a to b dx plus the integral of bx from a to b dx plus etc. all the way along, and of course that is going to be equal to minus the integral from b to a of a dx minus the integral of b to a of bx dx minus etc. etc., which then equals the integral from b to a of f, well, minus the integral of b to a of f of x dx. So, right, okay, they really haven't tested us very much on those first 4 parts, but there's plenty more to come, as I recall from splitting this across 2 pages. Suppose that f is any bilateral function. By considering the area under the graph of y equals f of x, explain why for any t greater than or equal to alpha, we have this relationship. So the integral of f of x from alpha to t is equal to the integral of f of x from 2 alpha minus t to alpha. Okay, so by considering the area under the graph. Well, we would do really, wouldn't we, if this is all integrals? So we can say the area under f of x between alpha and t is equal to the area under, well, it would be the area under f of 2 alpha minus x, I assume this is where we're going, between the transformed limits. As in, if we transform from f of x to 2 alpha minus x, then and we transform the limits, then we'll get the same result. So what are we doing on this then? So we're going from, what is the transformation? We're flipping in the, so we've got reflect in y axis, I should say, because we've got a minus x, and then we move 2 alpha to the right. So that means we're going from alpha to t. Then we're going to reflect in the y-axis. So that means we're going to go from minus t to minus alpha. Then we're going to move 2 to the right, which means we're going to go 2 alpha minus t to 2 alpha minus alpha. So that's just flipped our limits. So that's good. So we've got the integral from alpha to t of f of x dx is the integral from, now we're going from 2 alpha minus t to alpha of f of 2 alpha minus x dx, and f of 2 alpha minus x is f of x. So we've come full circle. So there's probably something quick you could write about reflections here. I mean, clearly we're just doing a reflection, one reflection. Okay, I've reflected in the y-axis and then moved it back to the right. But if we reflected somewhere else, then we just go from one function straight to the other, and then we can say, well, if it's just one reflection, we couldn't have changed the area. So there's always that possibility. Part 6. Oh, I've got to read this bit first, right? If f is a function, then we write g for the function defined by gt. G function of t is this integral. All right, so that was that bit there. So we're saying g as a function of t is equal to this. So it's going to be some, well, the area as we change t, because alpha is fixed. Okay, and that's for all t. Suppose now that f is any bilateral polynomial. Show that gt equals minus g 2 alpha minus t. Okay, let's write these out then. So gt integral from alpha to t of f of x dx. So g of 2 alpha minus t is then going to be the, well, actually, I'll put the minus in as well, why not? Minus the integral from alpha to 2 alpha minus t of f of x dx. Okay, so what are we then saying? Well, we've already done a lot of this, because we can say, if we've got this, then from parts, that was part 5, wasn't it? And the previous part, we can, well, that's allowing it. For the previous part, we're allowed to, as in part 4, we can now flip the limits round and get rid of the minus sign. And then we can transfer the limits back to be g of t. So we can say that that is equal to then the integral from 2 alpha minus t to alpha of f of x dx. So that's from part 4. And then from part 5, we can say that that is equal to the integral from alpha to t of f of x dx, which is equal to g of t. Is that everything? No, it's not everything. Oh, how annoying, because this is for t is greater than or equal to alpha, and that's for all t. So we need to have it then. So what about, so I need to put on here then that this is for t is greater than or equal to alpha. So now we need to do this again in some way for t is less than alpha. So what happens if t is less than alpha? How are we dealing with this then? What am I doing? If t is less than alpha, then what does that mean about 2 alpha minus t? That means that 2 alpha minus t is less than that, so that must be greater than alpha then. 2 alpha minus t is greater than alpha. So we can do this again then, but with 2 alpha minus t. I think that's what it's going to have to be, isn't it? So we'll be saying then that, actually, I mean, this works then, doesn't it? Doesn't it? Just wondering if this is the same thing then, because I've done g of 2 alpha minus t here, and if that is the case, then we're just okay with that. G of 2 alpha minus t, so put that into there, and we're saying in this top limit, yeah, so that's still fine. That would still be true because that's still bigger than alpha. Even if t is less than alpha, that still works, doesn't it? So actually, I don't think I need to do any more on this, actually. Let's see if this all, yeah, let's just double check. So as I'm going through this then we know we can flip the limits. Well, if I flip the limits afterwards, I think maybe that's the thing then that I can do. Because here we're saying we've got them the other way round. So if I do part 5 before I do part 4, then it definitely works. Because in this case, so if I just wrote this out, let's start with g 2 alpha minus t is equal to the integral from alpha to 2 alpha minus t f of x dx. And in this case, right, so 2 alpha minus t is greater than alpha, so that fits with this bit here. It's the statement of this, so that's what I'm doing. So that is then going to be equal to, so I need to do 2 alpha minus this, so that's going to be an alpha there. Now I have to do 2 alpha minus 2 alpha minus t f of x dx. Okay, so that is then the integral, the 2 alphas are going to cancel, from t to alpha of f of x dx. Yeah, so that's fine, which is, what am I trying to show? So I've shown that g of 2 alpha minus t is equal to, it's shown it is equal to g of t, haven't I? Oh no, because the limits are still the wrong way around. Yes, which is equal to minus the integral from alpha to t of f of x dx. So that is from part 4, and this is from part 5, doing this step here, and that step's from part 4. Okay, and then once again we've shown the same. I have done essentially the same thing. I've just done 4 and 5 different ways round, depending on whether I'm looking at t being greater than or equal to alpha, or 2 alpha minus t being greater than or equal to alpha. So that's come out okay, but something of a mess, and it's filled up the sheet, and I've still got one part to go. Suppose f is a bilateral polynomial such that g is also bilateral. Show that g of x equals 0 for all of x. Right, so if g is also bilateral, let's sneak in the middle here, that means that g of x equals g of 2 alpha minus x. But that's, yeah, and we've also got that g of x equals minus g of 2 alpha minus x. So add those together, and we've got 2g of x is equal to 0. So g of x is equal to 0. Right, okay, that last part was quite straightforward. I think that was a fairly tough question at the, well, certainly in the middle, the first 4 bits were pretty easy. The last bit was easy, but the 5 and 6 in the middle, I would have said, were fairly difficult. Well, particularly part 5, I think. But it does give the option of these because they're all show that. So if you can't get one part, you can just do the next bit. So there's going to be big chunks that you can pick up there, even if you haven't got the whole question right. I'm not personally a big fan of these question 3s, these function questions. They're fine, but we get one most years, it seems. I much prefer the question 4s, which are usually the geometry ones. Question 2s are usually quite interesting, but yeah, it's useful to be able to manipulate these functions in these different ways. When we start mixing them in with these areas and transformations and integrals and things. So yeah, they're sort of interesting, but not my personal favourites.